Yes friends, welcome once again to the class and welcome once again to the channel, and we are moving towards our next topic of discussion of today, that is Gamos theory of alpha decay, and this is the part 1 lecture of Gamos theory of alpha decay. So we will start the discussion today, and this discussion will go on up to the next class. Okay, so Gamos theory of alpha decay, that's what we are going to learn today. Now introduction. Why alpha decay cannot be explained by classical mechanics? We are going to learn that why. Okay, not how. It should be why instead of how. It is why. Okay, so why alpha decay cannot be explained by classical mechanics. So we will discuss that why alpha decay cannot be explained by classical mechanics. Okay, so let us see alpha decay and semi empirical mass formula. We are going to learn about this. Okay, so we have already seen that x is the symbol of the element which is undergoing decay. So this is your parent nucleus whose symbol is x, atomic number is z, atomic mass number is a. It is getting converted to daughter nucleus d having atomic number z minus 2, mass number a minus 4, and a alpha particle which has atomic number 2, mass number 4. So this is the alpha decay, and we will apply semi empirical mass formula on this alpha decay after some time. So the Q value or the total energy liberated in alpha decay. Now you have already learned that what is this Q, how Q is calculated for alpha decay, Q value of the process in alpha decay. You have already learned this. Okay, and when you try to actually open this bracket, when this c square will be multiplied by this entity, this c square will be multiplied by this entity, and this c square will be multiplied by this particular entity, then what happens? Along with this negative sign, if you consider this much entity, okay, if you consider this much entity along with negative sign and c square, then this particular entity is equal to binding energy for alpha particle. Okay, similarly along with negative sign, if you consider this entity along with c square in multiplication, then you will realize that it is the binding energy of daughter nucleus. And this particular entity over here, what is it? When you multiply it by c square, it has no negative sign, so that's why we will have to put one negative sign over here. So it is the binding energy of the parent nucleus. Okay, it is binding energy of parent nucleus. So you can write Q equal to B alpha plus B z minus 2 a minus 4 minus B z comma a, which is equal to B alpha means binding energy of alpha particle plus change in binding energy. Delta B means change in binding energy. Now this is the daughter nucleus binding energy, this is the parent nucleus binding energy. So the change in binding energy will be that when you subtract the binding energy of parent nucleus, from daughter nucleus. This is the binding energy of daughter nucleus, right? So from daughter nucleus, when you subtract the binding energy of parent nucleus, you will get the change in binding energy. Okay, so let me write over here. Let us write delta B. Okay, delta B is equal to what? It is change in binding energy. Change in binding energy means what? Change in binding energy simply means, okay, this is delta. Okay, this is delta. So change in binding energy simply means that you take the difference in binding energy of daughter nucleus and parent nucleus. So delta B is change in binding energy, which is difference in binding energy of daughter nucleus and parent nucleus. Okay, so when you subtract the binding energy of parent nucleus from the daughter nucleus, when you subtract the binding energy of parent nucleus from the daughter nucleus, you get something of this kind, that is delta B, which is change in binding energy. Just a second guys, just a second. Okay, just a second. Let me close the window. There is a lot of disturbance over here, so I will have to first of all close the window so that the voice is very clear. Okay, so I am closing the window. Yes, so the window is also successfully closed. So let's see difference in binding energy of daughter nucleus and parent nucleus. So that is your binding energy of daughter nucleus minus binding energy of parent nucleus. Okay, Okay, so this is the thing. So this is the binding energy of parent nucleus and this is the binding energy of daughter nucleus. So you are subtracting the binding energy of parent nucleus from daughter nucleus. This is the binding energy of daughter nucleus. So you are subtracting binding energy of parent nucleus from daughter nucleus. And that is your delta B. That is what? That is your delta B. And B alpha means binding energy of alpha particle, already told. The finite difference B Z minus 2 A minus 4 minus B means this is the daughter nucleus and this is the parent nucleus. So binding energy of daughter nucleus minus binding energy of parent nucleus is well approximated by corresponding derivatives. Now how do we approximate it? How do we approximate this particular thing? So actually the difference in Z is what? Difference in Z is Z minus 2 minus Z, that is equal to minus 2, that is equal to dZ. Okay. And what is the difference in A? A minus 4 minus A is equal to minus 4, which is equal to dA. Right. So dz equal to minus 2 because Z minus 2 minus Z is equal to minus 2 and A minus 4 minus A is minus 4. So that's why difference in Z is minus 2 and difference in A is minus 4, clearly from here. Okay. So what do we have then? So what do we have? So if you look at this particular derivative, you will realize that delta B can be written like this. Okay, delta B can be written like this. How? You can see this thing that dz is equal to minus 2. So over here you can substitute the value and look at it yourself. Okay, although it is wrong to say that you can substitute the value. Why it is wrong to say so? Because actually we cannot substitute the value over here because it is a derivative term. It is not a fraction. Del B by del Z is not a fraction. Okay, after all, del B by del Z is not a fraction. Similarly, del B by del A is also not a fraction. Okay, so that's why saying that substitute dz from here over here, substitute dA from here over here, and then check it yourself. Saying so is wrong. Saying so is wrong. But you can still do it for your convenience. You can substitute minus 2 over here and you can substitute minus 4 over here. What happens? Minus 4 cancel, minus 2 cancel. So you are left with delta B. You are left with delta B. Means minus del B. You are left with minus del B. So actually the binding energy, okay, delta B is what? Delta B is change in binding energy. Delta B is change in binding energy after the disintegration into daughter nucleus. After disintegration into daughter nucleus by emission of alpha particle. After disintegration into daughter nucleus by emission of alpha particle, we are getting the change in binding energy to be a function of. So change in binding energy is clearly a function of Z and A. Change in binding energy is a function of Z and A. Okay. So that's what is the meaning of this. So let us suppose this is your equation number 2. And this is an approximation. Okay. This is not very accurate. This is an approximation. Already it is written. Already it is written that this is an approximation. Now this is your equation 2. Using semi-empirical formula for B and experimental value of B alpha. Now semi-empirical mass formula you have already learnt in the previous classes. If you remember the expression for semi-empirical mass formula, what was it? You can go to the von Weizsäcker, okay, go to the lecture of von Weizsäcker semi-empirical mass formula, okay, semi-empirical mass formula. You can go there, you will find one lecture. Over there I have told you how to derive this formula. How to derive this particular formula. I have shown the derivation of this formula in the previous lectures. So in previous lectures you will find derivation of this formula. So using semi-empirical formula for B, okay, and experimental value of B alpha is 28.3 mega electron volt. So you are putting the value of B alpha over here. It was B alpha, right, in the expression. Over here it was B alpha. Over here it was binding energy of alpha particle. Okay, so binding energy of alpha particle was written over here. And what is happening? And the other terms you already know. What is AV, what is AS, what is AC, what is AA. These terms you have already learnt in the previous lectures. Okay, there is no need to tell them once again. If I tell them once again, then it is just a waste of time. It is just a waste of time. Okay. So this is the formula. Say by semi-empirical mass formula, the Q value can be written like this. Q value can be written like this with the help of semi-empirical mass formula. Okay. Now let us suppose that this is your equation number 3. Let us suppose this is your equation 3. Substituting the numerical values, it is found that now when will the Q value be greater than 0? Okay. when will the Q value be greater than 0? So let me tell you that the Q value, okay, the Q value should be greater than 0. Why it should be greater than 0? Because this decay will be stable. This decay will be stable only when there is mass reduction. Okay, when there is reduction in mass, only then this decay will be favorable, right? So the mass on the left hand side must be greater than the mass on the right hand side. Okay, so mass on left hand side must be greater than the mass on right hand side. So if we say that this is greater than the mass of these two things taken together, that is the value of Q is greater than 0, only then a nuclear reaction is feasible. So Q greater than 0, we will obtain Q greater than 0 only when the value of A is greater than 150 in this expression. In this particular expression, equation 3, only if you put atomic mass number A greater than 150, real life examples value you will put over here, right? So the value of Q comes out to be greater than 0. Value of Q comes out to be greater than 0 only when the value of A is greater than 150. Only then the value of Q comes out to be greater than 0. And only then alpha decay is feasible. That is the meaning. Okay. Only then alpha decay is feasible. Because Q value must be greater than 0 in order to have a feasible nuclear decay. The value of Q must be greater than 0. And value of Q can be greater than 0 only when value of A greater than 150 is put in this equation. Value of A greater than 150, if it is put in this equation, only then Q value comes out to be greater than 0. Otherwise Q value comes out to be smaller than 0. And when Q value comes out to be smaller than 0, what happens? When Q value comes out to be smaller than 0, then the feasibility of the process is not there. Okay, it is not an exothermic process then. If Q value is smaller than 0, suppose, then it is not an exothermic process. Then it is not exothermic. Okay, then it is not exothermic. So in order to have the process to be exothermic, Q must be greater than 0. Only then the process will be exothermic. Okay, only then the process will happen. Okay, because the energy will be reduced in the process. That's why Q value must be greater than 0. And only the Q value comes out to be greater than 0. The Q value comes out to be greater than 0 only when you put the value of A to be greater than 150 in this particular equation 3. Only then Q value comes out to be greater than 0. Otherwise Q value does not come out to be greater than 0 if we do not put A value greater than 150. If we do not put A value greater than 150, then Q value does not come out to be greater than 0 in this equation. Okay. If A value is less than 150, then what happens? The Q value also comes out to be smaller than 0 then. Okay. So if A is smaller than 150, then Q value also comes out to be smaller than 0. Okay. So this is not a feasible thing. So for Q value to be greater than 0, we must have A to be greater than 150, and if you put the corresponding value of Z over here, okay, then you will realize that after doing such calculations, experimentally doing such calculations, so after numerical value substitution, it is found that Q value is greater than 0 for atomic mass number A greater than 150. So Q value is 0 only for atomic mass number A greater than 150. Thus, nucleus having atomic mass number A greater than 150 are alpha unstable and suffer alpha decay radioactivity. So what is proved from here? From here it is proved that in order to have alpha decay, the minimum value must be 150 for atomic mass number. The minimum value for atomic mass number should be 150 so that alpha decay happens. Okay, only then Q value for alpha decay comes out to be greater than 0. Otherwise, it is not feasible. Okay, so that's why lighter nuclei do not undergo alpha decay. This implies that this precisely explains why lighter nuclei do not undergo alpha decay. Okay. Now, potential barrier which prevents alpha decay. Now let us understand the potential barrier which prevents alpha decay. Now, what are we learning right now? We are learning. Okay. We are learning that why classical mechanics fails to explain. Why classical mechanics fails to explain alpha decay. This is what we are learning right now. So let's understand about potential barrier which prevents alpha decay. Now Rutherford's alpha scattering experiment. Let us see. Plus ZE. What is the meaning of plus ZE? Plus ZE means atomic number is Z and charge on each proton is plus E. Okay, atomic number is Z and charge on each proton is plus E. So the overall charge on the nucleus will be plus ZE. Plus ZE. Okay, because Z is the total number of protons and plus E is the charge on each proton. So total number of protons is Z, charge on each proton is plus E. So the nucleus will have plus ZE total charge. So plus ZE is the total charge on this nucleus. And this alpha particle is being bombarded on this nucleus. Okay, plus 2E. This alpha particle has charge plus 2E. Plus 2E means charge equivalent to 2 protons. Plus 2E means charge equivalent to 2 protons. So this alpha particle is being bombarded according to Rutherford alpha scattering experiment. According to Rutherford's alpha scattering experiment, we are bombarding alpha particle on this particular nucleus, and this alpha particle has charge equivalent to 2 protons, and it is being bombarded. So it will approach the nucleus first. It will first approach the nucleus, and then it will revert back. So this is the point of collision. This is the point of collision. Okay. This is what? Point of collision. This is point of collision. So, because of Coulombic repulsion, the alpha particle came up to here and then it was reverted back. Because of the Coulombic repulsion between this plus 2E charge and plus ZE charge. Because of Coulombic repulsion, alpha particle came up to here and then was reverted back. And suppose this collision took place at a distance r. This collision took place at a distance r from the center of nucleus. From the center of nucleus, this collision took place at a distance small r. At a distance small r. If you keep on increasing the velocity of this alpha particle, if you suppose keep on increasing the velocity of this alpha particle, then what will happen? Then the alpha particle will come like this, even closer to the nucleus. Okay, and if you keep on increasing the speed velocity of this alpha particle, then the alpha particle will collide on the surface of nucleus. Getting it? If we keep on increasing the velocity of this alpha particle, then one day will come when the alpha particle will touch the nucleus. Okay, it will touch the nucleus. So such is the thing. So it depends on the velocity of alpha particle, that from where the alpha particle will collide and revert back. It depends on the kinetic energy of alpha particle. More is the kinetic energy of alpha particle, more nearer it comes to the nucleus. More is the kinetic energy of alpha particle, more nearer it comes. More is the velocity of alpha particle, more nearer it comes to the nucleus. Okay. So that is the thing. The exact nature of interaction between the alpha particle and the nucleus is not known. So the exact nature of interaction, as these are microparticles, so years of research is required to study them. Okay. As these particles are not visible with naked eye, so years of research are needed in order to study all these interactions between these particles. So exact nature of interaction between the alpha particle and the nucleus, if we try to understand the exact nature of interaction between that alpha particle and the heavy nucleus, so exact nature of interaction is not known, because these are all microscopic particles and we can only guess. Okay, we cannot actually 100% predict something, because we cannot see it with our eyes. Okay, because we cannot see it with our naked eye. So we have to do some experiments and infer from those results. So we guess two interactions. We can guess two interactions from here. So what are our guesses? Our guesses are that Coulombian repulsion might be there, and short range attractive nuclear force might be there. So when will the Coulombian repulsion appear? The Coulombian repulsion will act when the alpha particle is far away from the nucleus. Okay, so suppose the alpha particle is 10 to the power minus 10 meter away from the nucleus. Okay, so when the alpha particle is 10 to the power minus 10 meter away from the nucleus, at that time Coulombian repulsion will take place. But if the alpha particle comes so nearer to the nucleus, that the distance between alpha particle and the nucleus, it reduces to the order of 10 to the power minus 15 meter. Okay, or 1 femtometer. Then what will happen? Then nuclear force will also start to act. Okay, nuclear force will also begin to act in this particular case along with Colombian repulsion. Along with Colombian repulsion, nuclear force will also begin to act in this particular situation. Okay. So if you keep on increasing the velocity of alpha particle, if you increase the velocity of alpha particle somewhat, then what will happen? It will come nearer to the nucleus. But as soon as you make the velocity of alpha particle so high, that it comes so closer to the nucleus, that distance between the alpha particle and the nucleus reduces. Distance between the alpha particle and the nucleus reduces to the order of 10 to the power minus 15 meter. Then what happens? Then nuclear force, short range attractive nuclear force, will also begin to act along with Colombian repulsion. Okay, as already told to you. So we get two interactions: Colombian repulsion and short range attractive nuclear force. Due to rapid decline of nuclear forces with distance, okay, you already know that the nuclear force declines at a very higher rate with distance. Nuclear force is a very much short range force. It declines with increasing distance. Nuclear force declines with increasing distance. Due to rapid decline of nuclear forces with distance, what happens? Alpha particle will experience diminishing attraction near the surface of the nucleus. So near the surface of the nucleus, alpha particle will experience diminishing attraction. Okay. So if the alpha particle moves away from the center of nucleus, so what will happen? Actually, it will experience low attractive force. It will experience low nuclear attraction. Okay. It will experience low nuclear attraction. So that is what? Due to rapid decline of nuclear forces with distance, alpha particle will experience diminishing attraction near the surface of the nucleus. So alpha particle will experience diminishing attraction near the surface of the nucleus. At R equal to R, the nuclear attraction is balanced by Colombian repulsion. Now when you make the distance, this is what? This is your distance R, right? But this is the capital R, which is the radius of nucleus. Capital R is what? Capital R is radius of nucleus. So when alpha particle approaches the surface of nucleus, what happens? At that particular point, the value of small r will be equal to capital R. Okay. So at this particular point, what happens? At this particular point, actually the Colombian repulsion is equal to the nuclear attraction. So it is balanced. At the surface, the Colombian repulsion and the nuclear attraction is balanced. So let us write at the surface of nucleus, Colombian repulsion and nuclear attraction balance each other. So at the surface of nucleus, Colombian repulsion and nuclear attraction balance each other. At R equal to R, that is the surface of nucleus, nuclear attraction is balanced by Colombian repulsion. Thus the internal part of the nucleus is separated from the outer space by certain potential barrier. Okay, so you can understand this particular thing, that the internal part of nucleus is separated from the outer space by a certain potential barrier, okay, which prevents alpha particle to penetrate into the nucleus. Okay. So what is preventing the alpha particle from entering the nucleus? You can see over here. See, at this particular point, what is happening? You know that the radius of nucleus is of the order of 10 to the power minus 15 meter. Okay. Radius of the nucleus is of the order of 10 to the power minus 15 meter. Okay. So this is the order of radius of nucleus. You have already learned. Now, at this particular point surface, the Colombian repulsion is equal to nuclear attraction at this particular point. Okay. At that point. So up to here, if the alpha particle reaches up to here or up to here or up to here or up to here, what will happen? Up to those points, only the Colombian repulsion, Okay, at all these points, this point, this point, this point, this point, this point, at all these points above the surface, at all these points above the surface of nucleus, outside the surface of nucleus, the Coulombian repulsion will dominate. Coulombian repulsion will dominate. Okay, so let us write over here. This is suppose your nucleus. Okay, so on the surface of nucleus, on surface what will happen? Coulombian repulsion is equal to nuclear attraction on the surface. What will happen outside the surface? Outside the surface, Coulombian repulsion is dominating. And nuclear attraction negligible. Nuclear attraction negligible. And at a point inside the nucleus, what will happen? Coulombian repulsion is dormant. Okay, it will not act much. Nuclear attraction is appreciable. Okay, so at all these points inside the nucleus, what will happen? Constant potential will be there. Inside nucleus, because of homogeneity of nucleus. So there will be constant potential inside the nucleus according to classical model. Okay. The internal part of the nucleus is separated from the outer space by certain potential barrier which prevents alpha particle to penetrate the nucleus. So the alpha particle could not penetrate the nucleus because there was Coulombian repulsion which was creating the barrier. Okay. So height of barrier is equal to potential energy of alpha particle at the surface. At R equal to R means at surface. Okay. So minimum this much energy. Okay. When we provide minimum this much energy that the alpha particle reaches here. Okay. If alpha particle reaches here, if alpha particle reaches at surface, then what happens? Then if alpha particle reaches at surface, then potential barrier is crossed. Then potential barrier is crossed because this is the maximum energy which will be required. Okay, minimum energy. Okay, reaching over here will be the maximum reaching at the surface. Okay, alpha particle reaching at the surface. Alpha particle reaching at the surface of nucleus. Alpha particle reaching at the surface of nucleus implies what? Minimum energy. Okay. Required by alpha particle to penetrate the nucleus. So minimum energy required by alpha particle to penetrate the nucleus. Okay. Alpha particle reaching on the surface of nucleus. The alpha particle reaching at the surface of nucleus. What does it mean? Alpha particle reaching at the surface of nucleus simply means that it is the minimum energy which is required by alpha particle to penetrate the nucleus. Beyond this, if you provide energy greater than this, then what will happen? Then certainly the alpha particle will penetrate. Okay. So height of barrier is equal to potential energy of alpha particle at R equal to R, that is at the surface. The potential energy V of R of an alpha particle outside the nucleus at a distance R from the center of daughter nucleus is given by. Now you have already known this particular formula. This is 2E. Okay. So 1 upon 4 pi epsilon naught q1 q2 over r. What is the formula of potential energy? Potential energy of the alpha particle, potential between alpha particle and daughter nucleus, what will it be equal to? Okay, you can clearly see over here that potential V of r, the potential energy V of r between this alpha particle and this nucleus, what will it be equal to? It will be 1 upon 4 pi epsilon naught q1 q2. Okay, q1 q2, q1 is 2e, q2 is z minus 2e. Okay, q2 is z minus 2e. Why z minus 2e? Because daughter nucleus has z minus 2 as its atomic number. So 2e into z minus 2e divided by r. This is the separation between alpha particle and the daughter nucleus. So divided by r. Okay. So that's what we have written over here. That's what we have written over here. Okay. So 1 upon 4 pi epsilon naught 2 into z minus 2e q1 into q2 divided by r for r which is greater than radius of the nucleus. Okay. For all the points outside the means outside the surface, beyond the surface of the nucleus. Okay. R greater than r means beyond surface. R greater than r means beyond surface of nucleus. Beyond surface of nucleus. That means small r greater than capital R. That means beyond surface of nucleus. Okay. Now E into E, that will be E square. Z minus 2 is over here, 2 is over here. Okay. R is over here. 1 upon 4 pi epsilon naught, 4 pi epsilon naught is over here. Okay. So this is the thing. So you can see this thing. In case of uranium 92-238, what happens? We are taking one real life example now. So in case of uranium 92-238, what happens? The height of potential barrier of an alpha particle. Okay. So in case of uranium 238, at the surface, what will be the potential? At the surface of the nucleus, what will be the potential? That's what we are calculating. Okay. At the surface of the daughter nucleus, what will be the potential? So for uranium 238, which is undergoing alpha decay, what is happening? You will put capital R over here in order to find the potential at the surface of daughter nucleus emerging from nuclear decay of uranium 238. Okay. So this is what? This is potential at surface of daughter nucleus, from daughter nucleus from alpha decay of uranium 92-238. Okay, uranium 92-238. So when uranium 92-238 undergoes alpha decay, what happens? When uranium 92-238 undergoes alpha decay, one daughter nucleus will be formed. Out of it, and when that daughter nucleus is formed, the potential at the surface of that daughter nucleus, which is formed out of the alpha decay from uranium 238. Okay, the daughter nucleus which is formed after the alpha decay of uranium 238. See, after the alpha decay of uranium 238, one daughter nucleus will be formed, and the potential at the surface of that particular daughter nucleus, which is formed out of decay of uranium 238, we are finding that. Okay, so what have we done then? We have put, instead of small r, we have put capital R. Why? Because you remember the figure. Already, that you can see that this small r will be equal to capital R at the surface. So that's why small r equal to capital R. Because we are finding the value at surface. Okay. So this small r was here, it will be replaced by capital R. Now Z minus 2. Why? Because Z minus 2 is the atomic number of daughter nucleus. Okay. So the value of Z minus 2 will be what? 92 minus 2. Because parent nucleus has atomic number Z. As parent nucleus has atomic number Z and parent nucleus is uranium. So the atomic number Z will be 92 for uranium. And the atomic number for daughter nucleus is 92 minus 2 after alpha particle is emitted. Okay. So that's why 92 minus 2. And 1 by 4 pi epsilon naught is 9 into 10 to the power 9. Z minus 2 is 92 minus 2. E square. E is what? E is charge on proton. 1.6 into 10 to the power minus 19 coulomb square. Then R naught value 1.2 into 10 to the power minus 15, a to the power 1 by 3. A value for uranium, a value for uranium is 238. A value for uranium is 238. So 238 to the power 1 by 3. 238 to the power 1 by 3. Okay. So we have got the potential. Okay. You have got the potential at the surface of daughter nucleus to be 28 mega electron volt. You have got the potential at the surface of daughter nucleus to be 28 mega electron volt. So minimum this much energy will be required to emit the alpha particle from the daughter nucleus, okay, from the parent nucleus. Minimum this much energy must be applied, must be there in the alpha particle to exit from the uranium nucleus, okay, because this is the potential barrier. 28 mega electron volt is the potential barrier. The interaction in the nucleus may be represented by constant attractive potential U naught. Now inside the nucleus, already told to you, by nuclear shell model we have already assumed, okay, in the nuclear shell model we have already assumed that the potential inside the nucleus is constant. We have already assumed that the potential inside the nucleus is constant. Where have we assumed this? Where have we assumed that the potential inside the nucleus is constant? The potential inside the nucleus is constant. This particular fact we have assumed in the where? We have assumed this particular fact in nuclear shell model. In nuclear shell model. Okay. So interaction in the nucleus may be represented by constant attractive potential U naught exerted over distance capital R. So capital R is the radius of nucleus, and inside this nucleus there is constant potential up to here U naught. From here up to here constant potential U naught is there, okay, over the distance capital R. That is capital R is the radius of this particular nucleus. Capital R is the radius of this particular nucleus, okay. It is assumed as a potential well of depth U naught and width R. So it is very clear that this is potential potential depth, potential of well of depth U naught and width R. Okay. So width we can take 2R also. So it is like that. Hence V of R equal to minus U naught. That is R smaller than capital R. Okay. So at all these distances R is smaller than this R. This R is smaller than capital R. So capital R is the radius and this point is inside the nucleus. So it is smaller than capital R. Okay. So V of R is equal to minus U naught. Okay. Minus by negative sign because attractive potential. Okay. Minus U naught means attractive potential. Attractive in nature. Okay. So that's why minus sign. So V of R is equal to minus U naught for R smaller than equal to R. So inside the nucleus, this is suppose your nucleus. Okay. So inside the nucleus what happens? Actually it is not like this, it is like this. Okay. It is like this. Okay. So inside this nucleus, if you rotate, okay, this is a three-dimensional curve. This is a three-dimensional curve. You have to rotate about this axis. You have to rotate this curve about this axis. You have to rotate this curve about this axis. Then it will be a 3D curve. It will be a 3D curve, which is a valid curve. 3D curve is a valid curve. As we have the dimension of 2D over here on our screen. On our screen we have the limitation. On our screen we have the limitation of 2D drawing. We have the limitation of 2D drawing on our screen. Okay, we have the limitation of 2D drawing on our screen. That's why we are not able to show 3D curve over here. Okay, but in reality the curve will be 3D curve. You will rotate this curve about this V of R axis. Okay, V of R axis means potential axis about this. You will rotate this curve. You will rotate this curve and you will get one solid curve. You will get one solid curve. That is the actual curve. That is the actual curve. Okay. So the potential at all these points inside the nucleus. What is the potential? The potential is minus U naught because of attractive nature inside the nucleus, attractive nuclear force inside the nucleus. And as soon as you reach the surface of the nucleus, what happens? The Coulombian repulsion at this point, the Coulombian repulsion and the nuclear attraction are equal at this particular point. And after this particular point, the Coulombian repulsion begins to dominate, okay, which is reducing with distance now. Okay. So why now this particular value is 28 mega electron volt for uranium. for uranium, this particular potential barrier, this is what? This is potential barrier. This is potential barrier. So it is 28 mega electron volt for uranium. Means minimum this much energy of 28 mega electron volt must be applied. My minimum this much energy of 28 mega electron volt must be there in the uranium nucleus, so that it undergoes alpha decay. Okay. But in reality, it is found that alpha particle, okay, alpha particle never has this much energy. It is not possible. It is not possible for an alpha particle. It is not possible for an alpha particle to achieve. Okay, let me write. It is not possible for alpha particle to achieve 28 mega electron volt of energy. So it is not possible for alpha particle, it is not possible to achieve 28 mega electron volt of energy in practice. Means in experimental world. So that implies alpha decay will never take place. Alpha decay will never take place according to classical model. Because of height of barrier. Okay. According to classical model, because of height of potential barrier. Okay. So alpha decay will never happen according to classical model because of height of potential barrier. So in maximum energy which can be attained by alpha particle, is 9 mega electron volt. 9 mega electron volt is the maximum energy which an alpha particle can attain. 9 mega electron volt is the maximum energy which an alpha particle can attain. So to cross the 28 mega electron volt mark, is very difficult for the alpha particle, and it is not possible according to, if we rely on this classical model, then it is not possible that alpha decay will take place. Alpha decay will not be possible according to classical model because of height of potential barrier. Okay, but this is wrong. Okay, but we know, we experimentally see that alpha decay takes place. But we experimentally see that alpha decay takes place. Okay, but we experimentally see that alpha decay takes place. That implies our classical model, which says that alpha decay is not possible. Our classical model which says that alpha decay is not possible is wrong. Okay, is wrong inference. Okay, so that means that implies classical physics cannot explain alpha decay. Classical physics cannot explain alpha decay. Okay, we need quantum physics. To explain alpha decay. So quantum mechanical treatment of alpha decay. Okay, quantum physics treatment of alpha decay will be discussed in next class. Okay. So quantum physics treatment of alpha decay will be discussed in the next class. So quantum physics treatment of alpha decay will be discussed in the next class. So hopefully you got this concept, and you can go and watch the nuclear and particle physics playlist, the link of which is there in the description and in the form of end screen of this video also. So if you are new to this channel, then you can certainly watch from the very beginning and understand each and every concept very clearly. And please do subscribe to our channel, and please like the video. You guys are not at all liking the videos, you guys are not at all subscribing to the channel. Okay, so you guys are actually just from so many days, from 10-15 days, the number of subscriber is constant. The number of subscriber from 10-15 days is constant. So it is not a good sign actually. And when World Cup was going on, at the time when World Cup was going on, at that time you guys had stopped watching the videos. When World Cup was going on, ICC Cricket World Cup, when it was going on, you guys had stopped watching the videos. I was able to see it in the watch time. In the watch time of YouTube Studio, it was very low. So I was sure that you guys are watching the ICC Cricket World Cup. So all these are not good signs actually. All these are not good signs. Actually, you should be dedicated to studies for 1 or 2 years in order to clear UPSC. Thank you very much.